Hello students, welcome to online lecture 4 on chemical bonding. In this lecture, we are going to study about structure of solids. As we know that the matter exists in three different phases such as solids, liquids and gases. In solids, the particle arrangement is much closer as compared to the arrangement of particles in liquids and gases. Okay. Here we are going to focus more on structure of solids. So let us define solids. Solids can be defined as the state of matter which have definite shape and volume and have a rigid structure due to the closer arrangement of its constituent particles. There are basically two types of solids. One is crystalline solid and the other one is amorphous solid. Crystalline solids have highly ordered arrangement of its constituent particles, that is, they have certain definite geometrical pattern of arrangement of its constituent particles such as atoms, ions or molecules. Examples of crystalline solid are sulfur, sugar, sodium chloride, diamond, etc. Second type of solid is amorphous solid. Amorphous solids do not have a specific geometrical pattern of arrangement of its constituent particles. They are randomly arranged throughout the structure of solid. Example of amorphous solid are glass, rubber, plastic, peach, coal, starch, proteins are also examples of amorphous solids. Let us distinguish between amorphous and crystalline solids. As per the definition, amorphous solids have irregular pattern of arrangement of ions, molecules or atoms in a solid, whereas crystalline solids have regular repetitive arrangement of its constituents in a solid. Amorphous solids do not have specific melting point. They melt over a range of temperature, whereas having sharp melting point is a property of crystalline solids. Amorphous solids do not have definite heat of fusion, whereas crystalline solids have definite heat of fusion because of sharp melting points. Amorphous solids are called as isotropic solids because the property of material are identical in all directions. Whereas crystalline solids are called as anisotropic because the property of the material depends on the direction. Because of the regular, repetitive, specific geometrical arrangement, the property of crystalline solids depends on the direction. Therefore, it is called as anisotropic. Examples of amorphous solids are glass, rubber, plastic, peach, coal, starch, proteins, etc. Examples of crystalline solids are sulfur, sugar, sodium chloride, diamond, etc. As you can see from these images, this is a arrangement of the particles. These spheres can be considered as either atoms, ions or molecules. So these particles have definite geometrical pattern of arrangement in crystalline solids. Whereas you can see the arrangement of these particles in amorphous solid, it is randomly arranged. These particles are randomly arranged throughout the solid of amorphous. Now, based on the binding forces among the constituent particles, crystalline solids are basically classified into 4 different types: ionic solid, covalent solid, molecular solid, and metallic solids. These ionic solids consist of the array of positive and negative ions arranged in a definite pattern throughout its structure. Examples: sodium chloride, calcium oxide, magnesium oxide, calcium chloride. Many examples we can quote here. Then second type is covalent solids. Covalent solid consists of array of atoms arranged in definite geometrical patterns throughout the crystal structure. Example: diamond, graphite, silicon, etc. In molecular solids, the constituent particles are molecules. Okay, so these solids consist of an array of molecules specially arranged in a definite pattern of arrangement. Examples: iodine molecule, carbon dioxide, solid nitrogen, sulfur, phosphorus molecules are also the examples of molecular solid. Then fourth type of crystalline solid is metallic solid. This metallic solid, it consists of positively charged metal atoms embedded in a sea of delocalized electrons. Okay. So the binding force between the positively charged metal ions and electrons is electrostatic force of attraction in metallic solids. Examples: metals and alloys. Lattice and unit cells. This is an image of crystal lattice. What is crystal lattice? Crystal lattice is the highly ordered three-dimensional structure formed by its constituent particles such as atoms, ions, or molecules. Okay, so it's a overall three-dimensional structure extending in all the 3 axes, and the smallest repeating unit of this crystal lattice is called as unit cell, which is repeated again and again and extended in all directions to build up the whole crystal lattice. These are the definitions of crystal lattice and unit cell. Crystal lattice is a highly ordered three-dimensional structure formed by its constituent atoms or molecules or ions. Unit cell. It is the smallest building unit of a crystal lattice which, when repeated in different directions, generate the entire lattice of crystalline substance. There are another 2 terms which are associated with the crystal lattices, that is lattice point and coordination number. What is lattice point? It is represented as solid dot which indicates the position of an atom or ion or molecule in an unit cell. Next term is coordination number. It is the number of nearest neighboring atoms, ions or molecules bonded to the central atom of the crystal. Okay, so coordination number is the number with which the central atom of the crystal is bonded with. Now, as I said, there are seven crystal systems, of which we are going to study 2, that is cubic crystal system and hexagonal crystal system. Under cubic crystal systems, we have 3 lattices, that is simple cubic, body centered cubic and face-centered cubic. Let us first study simple cubic crystal lattice. Now this is a unit cell of a simple cubic crystal lattice. Okay, you can consider a box, okay, and three-dimensional box in which there are atoms present at every corner of the cube. Okay. So simple cube is a unit cell of cubic crystal lattice. Unit cell in three-dimensional lattice is represented by the axial length labeled as small a, small b and small c. These are the axial length along the xy and z axis, and the angle between them are labeled as alpha, beta and gamma. So these are called as unit cell parameters, and for simple cubic lattices these parameters are equal along the axis, that is A is equal to B is equal to C. Okay. The intercepts on all the axes are equal, and the angle between these edges are alpha is equal to beta is equal to gamma, which is equal to 90 degree. Coordination number in simple cubic crystal lattice is 6. So every corner atom is bonded with 6 other atoms of another unit cells, and the number of atoms per unit cell in simple cubic crystal lattice is 1. Example, polonium metal is the only metal which has simple cubic crystal lattice. These are the lattice points, okay, at the corner of cube. At each corner of the cube there are atoms present which are called as lattice points. So at 8 corners of the cube the atoms, ions or molecules are present. Second type of cubic crystal system that we are going to study is body-centered cubic crystal lattice, that is also called as BCC, body-centered cubic. This is a unit cell of BCC crystal lattice. Okay, at the corner of this cube atoms are present, so there are 8 atoms present at each corners of the cube, and there is one atom present at the center of the unit cell, that is inside the body of the unit cell. That is why it is called as body-centered cubic crystal lattice. Coordination number in BCC structure is 8, and the number of atoms per unit cell are equal to 2. Example, lithium, potassium, sodium, chromium, barium, vanadium. Again, as this is a cubic crystal system, the unit cell parameters A is equal to B is equal to C, and the angles between them are alpha is equal to beta is equal to gamma are equal to 90 degree. This is a unit cell of BCC crystal lattice in which all the 8 corners of a cube are occupied by the atoms, and at the center of the unit cell there is one atom present inside the body of the unit cell, which is represented as the red dot here in this unit cell. Okay. This shows the arrangement of the atoms in BCC crystal lattice. All the 8 corners of the cube are occupied by the atoms, and at the center of the unit cell there is one atom present which is not shared by any other unit cell. Third type of cubic crystal lattice system is face-centered cubic structure. Here is the unit cell of face-centered cubic structure. As it is cubic crystal system, again the unit cell is a simple cube in which at each corner of the cube atoms are present, and in addition to the corners, at the center of each face of the cube there is one atom present. So a cube has 6 faces. Okay, so along with the corner atoms, at the center of each face an atom is present. Coordination number in FCC crystal lattice is 12 and the number of atoms per unit cell in FCC structure is 4. Examples of FCC crystal system, that is gold, silver, iridium, aluminium, copper, lead, nickel and platinum. Again, since it is a cubic crystal system, the unit cell parameters are similar to BCC and simple cubic, that is A is equal to B is equal to C. All the axial intercepts are equal and the angle between them are equal to 90 degree. This is a unit cell of FCC structure. This is FCC unit cell in which every corner of the cube is occupied by the presence of. So these gray dots represent the corner atoms of the cube and red dots represents the atoms present at the center of each face of FCC unit cell. Now these are the types of crystal lattices that we have studied so far: simple cubic, body centered cubic and face centered cubic. Okay. So these 3 images signifies the lattice point locations as we have studied. In simple cubic, every corner of the cube is occupied by the atom. In BCC, along with the corner atoms, at the center of the unit cell, there is one atom present, that is body centered. And in FCC, at every corner of the atom, at every corner of the cube, atoms are present along with the atoms present at the center of each face of the cube. These images show the arrangement of the atoms in simple cubic, body centered cubic and face centered cubic. The next type of crystal system that we are going to study is hexagonal closed packed crystal structure, that is called as HCP, hexagonal closed pack. Hexagonal closed pack system can be visualized as the top layer of hexagon and bottom layer of the hexagon. Okay, you can see in top layer there are 6 atoms and the 7th atom fits in the middle of the top hexagonal face, and the bottom hexagonal layer there is one atom present in the middle of this bottom layer. Okay, you can visualize this as A layer, B layer and again A layer. So AB layer pattern is repeated in HCP type of crystal lattice. In HCP, the coordination number is 12 and the number of atoms per unit cell is equal to 6. Example: cadmium, magnesium, titanium, zinc, zirconium. This represents the unit cell of HCP crystal structure, and this image shows the arrangement of the atoms in HCP crystal lattice. So in this lecture we have studied these types of crystal lattices, that is cubic crystal system and hexagonal crystal system we have studied. Under cubic crystal lattices we have studied simple cubic, body centered cubic and face centered cubic. In simple cubic, coordination number is 6, number of atoms per unit cell is 1, and polonium is the only metal showing simple cubic arrangement. In BCC structure, coordination number is 8. There are 2 number of atoms per unit cell. Example: lithium, potassium, sodium, chromium, barium, vanadium. In FCC crystal structure, coordination number is 12. There are 4 atoms per unit cell. Example: gold, silver, iridium, aluminium, copper, lead, nickel and platinum. In HCP crystal lattice, coordination number is 12. There are 6 atoms per unit cell. Example: cadmium, magnesium, titanium, zinc, zirconium. Okay. So students, you should learn this table thoroughly, because in the exam the question is asked on coordination number and number of atoms per unit cell. Thank you very much.